Okay, so I'm going to pick up on the lecture that we had um, before the break. What we were covering was basically the chapter entitled "Mass Transfer." From This is essentially chapter 10 of Doran, and as I mentioned last time, this is just a brief review of it. Maybe I should go back and just refresh your memory. So, hmm, mm, okay. So, what we want to understand is we want to derive some expression for the rate at which oxygen moves from a bubble that is traveling through the liquid to a bacterial cell that needs the oxygen. And the same theory, if developed properly, should also tell us the rate at which carbon dioxide released by the cell gets back to the bubble, which then carries the CO2 up into the headspace. And I think I also did this example to show that because of the very low solubility of oxygen in water, it's about 8 milligrams, 10 milligrams per liter. That's the order of magnitude. Um, if you do not continuously supply oxygen, the oxygen will be depleted within a few seconds. And that is the reason why you need to know what is the rate at which oxygen is delivered. This is an important problem. And then I started off uh, by explaining this is the beginning of the theory. This is the whole picture of how oxygen moves from inside the bubble to the cell. And then I said that basically there is the line, the circle denoted 1 over here represents the movement of oxygen across the bubble. The circle 2 denotes the movement of oxygen within the liquid phase. And then 3 denotes the movement of oxygen across the cell. And uh, as I mentioned in my last lecture, um, the what is labeled 2 is generally not a rate limiting step because of we typically maintain turbulent flow. There's a rapid movement of oxygen due to turbulent flow. Little packets of liquid called eddies are thrown around that make the process quite fast. And in the case of cells, also we can ignore the the it's also not rate limiting because the cells are much smaller than the bubbles, and since their surface area is very high compared to their volume, they have no problem picking up the oxygen on their surface. Okay, so now with that background, we move now to actually determining a mathematical expression that describes the rate at which. So let me just give see if I can. Can't seem to find. Um, anyway, so let me just give a broad outline. What we want to show is that what we want to show. So we want to show we want to show that the flux and fluxes in moles um, is in moles per hour per meter square or centimeter square. So this is per unit area flux per unit interfacial area between the bubble and the liquid. we want to show that the flux in moles per hour per unit interfacial area is given by an expression and of the form, this is given by an expression. So if I denote the flux by J, right, this is in moles per hour per centimeter square or per meter square. This is equal to the final expression that we will derive will be KL multiplied by C in the particular, we will allow A to be any component, any gas. It can be oxygen, or it can be CO2, or it can be nitrogen, or whatever, minus Ca, where this concentration is the concentration of, of gas A in the bulk phase. In the bulk phase. And the bulk phase, as I pointed out to you last time, was not in the boundary, but in the bulk. So in the bulk liquid, how much gas do you have? For us, in the case of oxygen, this quantity is also called dissolved oxygen concentration. Dissolved oxygen concentration simply means the concentration of oxygen in the liquid phase, in the bulk liquid phase. And this quantity, Ca star, it's a slightly complicated property, a slightly complicated concentration. It's a hypothetical concentration, the meaning of which will become clear um, as we move on. So now note that this is defined in terms of per meter square. This is per meter square of the interfacial area between the bubble and the liquid. So if A denotes the interfacial area, if A denotes how much interfacial area you have per unit volume of liquid, then basically by multiplying both sides of the first equation, you can see that basically um, the rate of oxygen transfer, right, in moles, this is J times A, that has units of moles per hour, right? And this has units of meter square per meter cube. So that's 1 over meter. And so you get J times A as units of, actually, maybe instead of meter cube, it's a little awkward. Probably work with liters. This is the more common unit that we work with. So this becomes, sorry, my mistake. This should be per, yeah, we have to work with it, centimeter square, and then this becomes J times A becomes per centimeter cube, which is equal to KLA times Ca star minus Ca. So this is going to give you the moles that are transferred per hour, the rate at which oxygen is transferred per unit volume of the liquid in the reactor. This expression will play a very important role when we set up the mass balances for oxygen. So this is what we are after. So we will begin by deriving a theory that first of all gives this expression. Now there are, I should point out, more than one theory, all of which lead to the same expression, but they give different formulas for this quantity KL. Um, there are also theories for telling you how to predict the interfacial area A, but I don't think we'll have the time to get to it. So let's start with the first, which is, let's see, A. This is what is called the film theory for the mass transfer coefficient KL. Or I should not say mass transfer coefficient, for oxygen transfer. for gas liquid mass transfer. Okay, so um, the the picture we have in mind now, I'm blowing it up. Previously, we have shown that we only need to worry about things that are happening when the gas is moved from the bubble into the liquid, right? We did not worry about what is happening in the liquid. We need not worry about what is happening when the gas goes from the liquid into the cell. So we're focused only on the movement of gas um, from uh, the gas phase inside the bubble to the liquid that is surrounding it. And so this is the bubble, and this is the surrounding liquid, and there is air inside the bubble, and this is the only movement that we are concerned about. All other resistances are negligible, which I will blow up, right? This picture I will blow up, and I will say, let's say, this is the gas or the bubble phase, and this is the liquid phase. Now, the film theory assumes that there is a stationary. Actually, all the theories assume that there is a stagnant or quiescent film on either side. So this is uh, you can call it boundary layer or film or whatever you want to call it. There is no relative motion between the liquid, for instance, over here, and the interface. It's kind of stationary. Okay. And the notation that we will use for the concentration in the bulk gas is the concentration. This is the concentration of gas in will be denoted pi A, where pi A denotes the partial pressure. This is the partial pressure of the gas A. Once again, we will almost always A will be oxygen, but in general, this theory applies to any gas. Any gas. Okay. And of course, in the liquid phase, here is a concentration in the bulk phase, which is Ca, which will often be in millimoles per liter, or grams per liter, or milligrams per liter. Okay. And why have I drawn a horizontal line? Because the film theory says that uh, only in the stagnant. So basically, the assumption is that uh, here, as we have already talked, this is the bulk liquid region, and this is, you can say, the bulk gas region, which is inside the bubble. And we are assuming that these areas are well mixed, and so there is no concentration gradient over here. The entire concentration gradient lives only in these thin films. So basically, here you will have a concentration drop like this. So it goes from pi A to this concentration here, which is labeled pi A I. I is for interface. So this is the partial pressure of the gas A at the interface. Okay. And as we will soon make more precise, at the interface, the concentrations of the gas and the liquid are in equilibrium for reasons I will just give in a minute. So here you have the concentration CAI, which is the concentration of the liquid, of the gas and the liquid at the interface, which is in equilibrium with the concentration of A in the gas phase. And then this comes down like this. Okay. Now, before I proceed, you may ask me, why am I going through all these gyrations? I mean, um, why don't I just take the difference between the concentration in the bubble and the concentration in the liquid and close the matter? Like, just take the difference of oxygen in the bubble minus the concentration in the liquid, take that gradient, right? Multiply it by some constant and say that is the rate at which the flux is taking place. So any thoughts on that? Why are we going through all this crazy stuff where we split it into two phases and then we say there is an interface in the middle? Why don't we just take what I have called pi a minus ca multiplied by some constant and say that is the flux across the bubble? Any thoughts? Anybody? Any take a shot at it? Just a wild guess. So has this been taught at all in Bhaskarvar's course? What I'm talking about? Wow, am I even audible? Hello, is anybody there?
Yes, sir, you're audible.
So has anything along these lines been discussed in the mass transfer course? This is actually a theme that is repeated over and over again in mass transfer. So I'm just asking, um, has this been covered in any way, shape, or form in mass transfer?
No, sir.
Okay, so then um, go back. So the reason why we are going through all this is that if you're wondering why we have separated this, uh, concentration. The main point here is difference of concentrations is the driving force is the driving force for mass transfer only in a single phase. In other words, as long as I am in the gaseous phase alone, or as long as I'm in the liquid phase alone, only then can I say that the flux will be proportional to the concentration gradient. The moment I have an interphase transfer from one phase to the other phase, it is not the difference of concentrations that drives the flux. It is actually a quantity called chemical potential, which is covered in, I guess, thermodynamics, which does not have any simple relationship to the concentration. So that is why we are forced to split this problem into two parts, right? We're going to use very soon concentration gradients, which provide a good estimate of the flux on one side or the other side, but cannot be used to estimate the flux from one side to the other side. I mean, the concentration going from the bubble to the liquid is simply not proportional to the difference pi a minus ca, right? The flux within the bubble is going to be proportional to pi a minus pi ai. It is also going to be proportional to cai minus ca, but you cannot say that it is equal to pi a minus ca. That is simply wrong. Thermodynamics tells you that the driving force is not the concentration, it is what is called the chemical potential. And in fact, actually, things can move from a lower concentration in one phase to a higher concentration in the other phase. There are examples of, if I remember correctly, for example, if you think of some volatile substance like benzene dissolved in water, um, even at relatively low concentrations of benzene in the water, that's highly volatile, it will move towards the gas phase, even when the gas phase concentrations are quite high, right? So the driving force is not the concentrations in the two different phases. You have to come up with something else. Anyway, so if that is clear now, let's move on forward. So the film theory assumes, so the film theory assumes, uh, first, that the bulk of both phases are well mixed. Both phases, meaning the bubble phase and the liquid phase, are well mixed. And that is why we have noticed the fact that we have made pi A and Ca totally flat and constant. They're well mixed, means there are no concentration gradients here. Okay? So hence uh, profiles for pi A and Ca, the concentrations in the gas and the liquid phases, are constant. The second assumption is that near the boundaries, near the interface between the two phases, both near the interface, both gas and liquid are quiescent or stagnant, i.e., there is no convection. So that means all you have is pure diffusion there. Now, another two more assumptions are made. So if we assume furthermore that there is no reaction in the films. So why is that important? So for example, in our case, we're dealing with oxygen, right? Now, in the liquid phase, you have actually little cells floating around, right? The cells live in the liquid phase surrounding the bubble. In principle, you could also have cells within this thin boundary. And these cells within the thin boundary could consume oxygen. We are neglecting that consumption of oxygen. And I'll tell you how we will use it in just the next line. So we're assuming that there is no reaction in the films. And we also assume that the concentration profiles are at steady state. Now, this again, second assumption also I will. So, actually, in reality, what is going to happen is, you have liquid that comes and moves along the bubble like that, and then kind of goes like that. This is the path of the liquid, right? And one can imagine that initially, at some initial part, um, maybe the liquid, there is some transient, but as the liquid flows along the bubble for a long period of time, there is a long contact between the liquid and the bubble, then the concentration profiles that define what is happening inside the boundary stabilize to a steady state. And that is the assumption being made here. This assumption is relaxed. It's not quite right, so it is relaxed in a subsequent theory that we'll get to in a minute. But for the time being, if we assume, furthermore, that there is no reaction in the film and the concentration profile is at steady state, then basically what you have is, I mean, if I can write down here, you know, from transport phenomena, you know that this is, if it's one dimensional flow, let's say uh, this is dCA dZ equals d times d squared Ca dZ squared um, plus or whatever some reaction term. Yeah, some reaction term here. So basically, what we are saying is, first of all, because we are on the film, we said that this convective term is equal to zero, right? There is only pure diffusion. Second thing, we said that there is no reaction, so we threw away the reaction term. There is no oxygen consumption taking place in either one of the two films. And if it is, basically it is so small that we can assume it to be equal to zero. And the third assumption is that the whole thing is at steady state. So we this put this equal to zero. So what we end up with is essentially zero equals d times d squared Ca by dz squared in each of the films. And that is just Fick's law, Fick's second law. Well, if d squared Ca dz squared is equal to zero, then that means that basically dCa dz is constant, right? So it means that the concentration profiles inside the film are straight lines, which is exactly the way I have drawn them. This comes about because of the two assumptions that we have made, that there is no consumption and the profiles are at steady state. So that means that with these assumptions, I can say, so let's say this represents Jg, the flux in the gas phase, and this is Jl, the flux in the liquid phase. So since they are both linear, I have Jg, so it's pure diffusion. Jg is going to be equal to, let's say, dA comma G is the diffusivity of the gas, right? Is the diffusivity of the gas A in the bubble. Okay? Then you basically get this expression divided by, and this Lg is the thickness of the film. So let's say this is Lg, the thickness of the stationary film in the gas phase, and this LL is the thickness of the stagnant film in the liquid phase. Then basically the flux in the gas phase is just the diffusivity multiplied by the concentration gradient. Okay, this is coming about simply because Fick's second law applies under the assumptions that we have made. And similarly, you can say that JL is equal to DAL, where DAL represents the diffusivity of A in the liquid phase. And of course, this is the concentration gradient, which would be CAI minus CA divided by LL. Now, it turns out that it is convenient to combine these two quantities, and you write this as K. I guess you should actually, strictly speaking, write KAG, but I will simply use KG um, multiplied by pi A minus pi AI, and this is written as KL multiplied by CAI minus CA. This Kg is called, the name for this is called the gas side mass transfer coefficient. And this KL is called the liquid side mass transfer coefficient. So the mass transfer coefficient is nothing but, according to this theory, the diffusion coefficient divided by the thickness of the film. Okay. And so what are the units? You can see that, take the case of Kg, which is defined as DAG divided by Lg. Diffusivity has the units of meters square per second. And this has units of meter. So Kg has units of meters per second. Okay. And similarly, KL has units of meters per second. Because once again, it's the ratio of the diffusion coefficient divided by the thickness of the film. Okay. Now, the next assumption that we make, uh, is that the boundary between the two phases, which is to say the bubble and the surrounding liquid. So the interface between the two phases is so thin that one, it cannot accumulate or store any gas A. That means that basically you must have Jg equal to Jl. So coming back to this picture here, the only way Jg, which is the flux across the quiescent film on the gas side, will not be equal to the flux Jl on the liquid side is if the film starts to accumulate, is capable of accumulating oxygen or whatever the gas be in question. But in this case, we're assuming the film is so thin it cannot accumulate anything. If it cannot accumulate anything, then Jg has to be equal to Jl. There is nothing that can create any kind of inequality between Jg and Jl. The second point is that if this film is very, very thin, then basically it rapidly equilibrates. And that means that the interfacial concentrations are in equilibrium, which basically means that the two concentrations are related by an equilibrium constant, which in this case is the Henry Lawes constant. So this is in equilibrium. This is an equilibrium relationship, and this is called the Henry's law constant. So it basically says that if you have so much, say, gas A in the liquid phase, then this must be the concentration of the gas in the gaseous phase, right? So, for example, if you have so many moles per liter of oxygen in water, then you put it in contact with air, then the air will have so much partial pressure, right? That's sort of the relationship between the two. And this Henry's law constant, as defined, Henry's law constant is a measure. This is important, of the insolubility of the gas. not the solubility, but the insolubility of the gas. Why? Because you can see it by just drawing the picture. Here you have the partial pressure, and here you have the concentration in the liquid phase. So this is in millimoles of oxygen, for example, per liter, and this is in atmospheres. Now, this is the picture for highly soluble gases, and this is the picture for gases that are so high values of the Henry's law constant indicate insolubility. To see that, just it's simple to just draw a horizontal line. Basically, this is the line with high slope corresponds to insoluble gas, and the line with low slope corresponds to the soluble gas. To see that, simply take a fixed, say, for example, partial pressure of A in the gas phase, and basically you can see that in the case of the insoluble, yeah, you will get a very low value of CAI. In the case of soluble, you will get a high value of CAI. So HA is actually a measure of the Henry's law constant defined this way, is a measure of the insolubility of the gas. So, for example, to be more precise, HO2, which is highly insoluble, is 790 atmospheres per this is moles per liter, whereas HCO2, which is highly soluble, is around 30 atmospheres per mole per liter. So is that part clear? I mean, this is something that we will need later on. I should point out that this is not the only way the Henry's law constant is defined. Actually, um, in atmospheric sciences, they define it the other way around. So stated differently, we have defined HA as the ratio of the concentration in the gas phase divided by the concentration in the liquid phase. And in if you take a look at the literature, this is often referred to as volatility constant. But among the atmospheric scientists, this is often defined the other way around. They define it as CAI over pi AI. So they just invert it. And then they call it solubility constant. Because the moment you invert it, then HA becomes a measure of how soluble it is, in fact, instead of how insoluble it is. So I hope that that is clear. Any questions so far?
No, sir.
Is it clear?
Yes, sir.
Yes, sir.
So now we're now ready to close the. So basically, this assumption implies. So I should maybe number it. If I call this 1, I call this 2, and I call this 3, then, and I call this 4. Then basically by 3, which is the fact that the two fluxes are equal, from 3, so since Jg equals Jl, and that is because the thin interface cannot store anything, we have, this is saying that Kg multiplied by pi A minus pi AI must be equal to KL multiplied by CAI minus CA. This has to be true. This is because the fluxes are equal. Now, but we also know, but we also know by equilibrium, so we also know that by equilibrium that pi AI, right, is equal to HA multiplied by CAI. This is by equilibrium. So basically we have two equations, this equation and basically this equation 4. This is equation 4. And if we solve these two equations, we can there are two unknowns here. So we think the way we are thinking, we solve concentrations. There are experimental ways of measuring this and this. What we don't know are this and this. It's really hard to measure interfacial concentrations. I mean, what kind of a probe would you take to just go and touch the interface? It's kind of hard to do that. But because of the way we have set up the model, we have two equations and two unknowns. So basically, you solve for the two unknowns. So solve for so two equations with two unknowns. The unknowns being CAI and pi AI. Given these two equations, you can solve for these two unknowns. Plug these unknowns back into this equation over here. That means if you solve for pi AI and CAI, you can plug them in, and that will give you the fluxes. So that's the theory. That's all there is to it. That is the background to it. Now, let's proceed. I think so. What I'm talking about here is, in other words, so for example, take this relationship pi AI equal to HACAI, plug it into the first equation, and you get kg multiplied by pi A minus HA, right, multiplied by CAI. So I'm replacing pi AI by HACAI. That is equal to KL multiplied by CAI minus CA. So now I have one equation in one unknown CAI. You can solve for CAI, and I will not go through the algebra. I'll simply say the final result. It turns out that CAI, you solve it, it turns out to be equal to Kg times pi A plus KL times CA divided by Kg HA plus Kg. Now, once you have pi A, once you have CAI, then you can also find out what is pi AI. That, of course, use the second equation, this one over here, and this is nothing but HA multiplied by CAI. And if you go through all the mechanics, find out that this is just HA multiplied by Kg pi A plus KLCA. This is Kg HA plus Kg. That's it. So you just solved for CAI and pi AI, which are the two quantities that are difficult to quantify, difficult to measure. But the model was set up in such a way that it actually gave you these difficult quantities. Now substituting, so let's say now what we really want is an expression for the flux. That means we want to take these two expressions over here and plug them into, where is it? We want to plug them into these equations. Once we plug pi AI and CAI into these, we will get expressions for the flux. Yeah. Now we have two different ways of getting these, right? We can either plug the expression for pi AI, that will give us one expression, or we can also plug the expression for CAI, and that will give us another expression. Now I will do one of them, which is plug for CAI, and then I'll simply give you the result for the last case. So we can substitute we can substitute pi ai and cai expressions, right? We can substitute these expressions into the formulas for J, G, and JL. So let's start. Well, we have JL, right? What was my notation? JL? JL. JL was equal to KL multiplied by CAI minus CA. And I will substitute this expression that I have found. So this I will write as KL multiplied by KG pi A plus KL CA divided by KGHA plus KG minus CA. That's it. Now you can see, sorry, there is a mistake here. This should be KL. Okay. And this also should be KL. So this KLCA and KLCA will cancel out, and you will end up with KL multiplied by, this will give you KG pi A, and here you will get uh, minus KGHACA, the whole thing divided by KGHA plus KL. And with a little bit of, you can see that this can be written as KL multiplied by KG divided by KGHA plus KL. And this thing can now be written as pi A minus, and here you get HA um hmm. oh KG. I hope this should be, I took CA. Did I make a mistake somewhere? Is this okay so far?
Yes, sir.
Oh, okay. All right. Okay, no, that's okay. No, this is fine. I just have to make a slight change here. This is, this is, I'll tell you what. This is pi A over HA minus CA, and that is divided by KG over HA, sorry, KG. So, it'll be KG plus KL over HA. So, now this can be written as KL times KG divided by KG plus KL over HA, and this becomes pi A over HA minus CA. Now, here is the important point. What is this quantity? Yeah. Now, this quantity is that concentration in the liquid phase, which would be in, so recall that pi A, going back here, this is a hypothetical quantity. Keep in mind that pi A was the concentration of the gas A in the bulk phase of the gas, right? It's the concentration over here. If I take pi A divided by HA, I am basically trying to find out that concentration of the gas A in the liquid phase that would be in equilibrium with the concentration or partial pressure pi A in the gas phase. So this quantity is denoted C A star. And what does it mean? It is a hypothetical. C A star is, it's not a real concentration. It is a hypothetical. It is a hypothetical liquid phase concentration, liquid phase concentration, right? That would be achieved if the bulk, if the bulk of the gas phase, say, were allowed to equilibrate with the gas phase, sorry, with the liquid phase. So this is not a real concentration, right? We have basically, if you will, multiplied pi A by a constant, which is actually 1 over HA, that basically transforms pi A into a liquid phase concentration. So we're basically going to go to this graph here. So let's say if this is the graph for, oxygen, basically we are going to go to the bulk phase concentration, pi A, we're going to, and find out, we know what pi A is. And from this graph, this will give us what CA star is. So keep in mind, this is not a real concentration. This is not, by real concentration, I mean that this is not a concentration that is there in the concentration profile. It is simply a hypothetical concentration. Is that part clear? So then we can move on.
Yes, sir.
So far, it's clear?
Yes, sir. It's clear. Yes, sir. It's a hypothetical concept.
So now you can do, we did this by plugging in for CAI in the expression for JL. But the same thing can be done, and this I will not do, I will leave it to you. So we can, so maybe I should actually pause here for a second and rewrite this. Maybe I should also mention a little bit about this quantity here. This quantity here, this is called the overall, right, mass transfer coefficient. Overall. So notice we had defined KL and KG as liquid side and gas side mass transfer coefficients. But these are called overall because, it takes into account everything. Yeah. So this is an overall mass transfer coefficient. Wait a second. I should actually say overall. I called overall liquid side mass transfer coefficient. And why is it called liquid side? It's called liquid side because the concentration gradient here is entirely on the liquid side. C star is a hypothetical concentration, but it is after all a concentration in the liquid phase. And we'll just, derive the analogous expression for the gas phase, the overall gas side mass transfer coefficient. So this is, you can see, this is often denoted, this whole thing is often denoted by capital, it is denoted by capital KL, L for liquid side. And you can see that capital KL, if I divide both the numerator and the denominator by KL kg, so you can see that KL can in fact be written as 1 divided by 1 over KL plus, and this will be 1 over HA and 1 over kg. Okay, this is one way of, this is this is this is the expression for the overall. Now instead of, so if, I'll just repeat it. So if we substitute, this is just running, doing the same thing in parallel. If we substitute the expression for pi AI, right, in the flux, so now I'm, Jg was written as Kg multiplied by pi A minus pi AI. So if I take the expression for pi AI, what we just did earlier was take the expression for CAI and plug it into the expression for JL. Now I'm taking the expression for pi AI, which is this expression over here, and plugging it into the expression for JG. And I'll let you do this on your own. Okay, we find that, see that basically you will get the expression. This is another way of expressing the flux. You will find that Jg equals, uh, let's see, it'll turn out to be Kg multiplied by, this is the analog, pi A minus pi A star, where this again, where pi A star is again a hypothetical concentration, which is basically, this is equal to HA times Ca. So this is that concentration in the gas phase that would be in equilibrium with the real concentration Ca that is observed in the bulk of the liquid phase. Okay? And Kg, it turns out, will be equal to KGKL divided by, this is KGHA plus KL. Or you can, by dividing the whole thing, you can put it in another form. This is equal to 1 divided by, and this becomes HA over KL plus 1 over kg. Okay, so either one of these two expressions can be used because JL is equal to JG. Now, it turns out we will almost always be working with this expression over here. Where is it? This expression, JL. So we will almost always be working with this formula, which is JL is equal to JL, or we need not talk about JL and JG because they're both equal. So we'll just call it J. Um, and this is the expression. Now there is another important simplification that results if the gas is highly insoluble or the gas is highly soluble. Okay, actually I'll tell you, just take a look at it. So let's take a look at this expression over here, the one over here. This is actually the expression for JL. Now suppose the gas is highly insoluble, which I have just pointed out to you earlier, means that HA is very large. Let me return to this. I just told you that when the slope is very large, we are dealing with an insoluble gas. And when the slope is very small, we are dealing with a soluble gas such as CO2. Okay. So let's first consider the case of a highly insoluble gas like oxygen, which has a solubility of barely 8 milligrams per liter. Since HA, right, is very small, then basically, where is it? Hmm. Um, mm, that's KL is equal to kg. I mean, oh, I made a mistake somewhere. Uh, KL should be equal to 1 over KL plus, I'm getting kg over, uh, this expression is correct. Hmm. Yeah. Hmm. Huh. Okay. Okay. So here it is. So suppose HA is very large, right? If HA is very large, first I'll do it mathematically and then I will explain to you physically. Then basically it means that this quantity can be neglected, right? So let's consider two special cases. So special cases. So one is gas is highly soluble, is highly, sorry, insoluble, such as oxygen, such as oxygen, which has HO2, as we remember, was I think around 3000, almost 800. It is around 800 atmospheres per moles per liter. Right. So if H is very large, you know, we just discovered that capital KL becomes almost equal to small kl. So we had, let me repeat that expression, Ka as equal to 1 divided by 1 over KL plus it was H, what was it? Mm, plus 1 over kg, 1 over kg, and this is HA. So if HA is large, we neglect this, and KL is approximately equal to small kl. Now, what am I saying here? Basically, what we are saying here is that if the gas is extremely insoluble, then going back to this picture over here, which I gave at the beginning of the class, we are basically saying that all of the resistance is actually over here, and that the resistance over here is negligibly small, right? So the gas is insoluble. Most of the resistance resides. So right now we are accounting for both films. But if the gas is highly insoluble, then we need not even worry about the inner film. We need only worry about the outer film. So what is the picture that we will then get? The picture will become much simpler. This is the picture we will get. So if this is the interface and this is the film and this is the film on the right hand side. Earlier we had a picture where it was straight and then it went down sharply. This is the gas side, this is the liquid side, and this is the interface. But now, because most of the in the face of insoluble gases, the decline only takes place. So this will not change at all. This will be basically horizontal. So this is essentially pi a is going to be approximately equal to pi ai. Nothing is going to change here. And then this is concentration. There will be a decline here, and this will go to Ca. So this is the picture if the gas is insoluble. On the contrary, the second case is if the gas is highly soluble, as was the case for CO2, which had a Henry's law constant, HCO2 was equal to, was it 7? I think a low number of um, uh, HCO2 is 30 atmospheres per mole per liter. So now HA is very, very small. So go back to the expression for kg, which I haven't gone through completely. But if HA is very, very small, this is the expression for kg. And you can see that if HA is very, very small, then this disappears. And kg, so if HA is small, then kg becomes approximately equal to kg. And this is the same logic, right? So basically, so if HA is small, then the overall gas side transfer coefficient becomes approximately equal to kg, and J, I'm just going to use J because both are the same, is approximately equal to kg multiplied by pi a minus pi a star, where pi a star was defined as HA times Ca. So what happens if the gas is highly soluble is that all the resistance is on the gas side. Okay. So if the gas is highly soluble, as it makes sense, then the resistance shifts to. So now you will have the picture. What we are basically saying is, now you will have the picture. Here you will see a sharp drop, and this is pi a, and this is pi a I. But here, let's say it's CAI, the interfacial concentration, but there'll be nothing here. It'll be like this. So there's virtually no drop on the liquid side. So depending on the solubility of the gas, one of the films becomes irrelevant. If the gas is highly soluble, then the liquid side resistance becomes irrelevant. And if the gas is very, very poorly, it's basically insoluble, then all the resistance shifts to the liquid side. Is that part clear? I think that is the main. So we will always be working. If we work with oxygen, which is what we will do going forward, we will always be using this expression. We will be using this expression: J equals KL multiplied by C A star minus C A, where this is, I guess, pi A divided by HA. That is what we'll be dealing with. Is that part clear? Let's just check. Any questions?
So it's clear.
Okay. So now, uh, so now, uh, as I told you earlier, J has units of moles or millimoles per hour per centimeter square, or right, this is per centimeter square of, this is the interfacial area, right? If we multiply J, so J multiplied by the interfacial area, the interfacial area per unit volume of liquid, right? Then that will give me essentially millimoles or moles per hour per centimeter cube or per liter. This will be of liquid. And that's the quantity that we will work with, right? So this is actually, this quantity is actually called A. The small a stands for interfacial area per unit volume of liquid, and it has units of a centimeter square by centimeter cube. So clearly a has the dimensions of 1 over length. Okay, so basically what we actually have is, if we want to calculate, so if we want to calculate oxygen transfer, so this is, all this is being done to calculate the rate at which oxygen is being transferred from the bubble to the liquid. And so rate at which O2 is transferred from gas to liquid, and in fact to the cells as far as we're concerned, because we claim that the resistances uh, from the liquid all the way to the cells are nearly zero, is, so this is actually, in fact I should even correct it and say, although our expression, what the hell is going on? Okay, so to liquid, in fact to cells, is going to be KL. We had earlier this expression KL multiplied by CA star minus CA. We'll multiply that by A to get the expression KLA multiplied by CA star minus CA, which now has units of moles per hour per liter of culture, per liter of medium, per, this is the constant, this is the volume of the liquid phase, right? Because A has dimensions of interfacial area per unit volume of liquid. Now, actually, it turns out that it's very difficult to measure either KL or A separately. I mean, there are ways of doing it, but they're kind of tedious. So actually, we always treat this as a single quantity. Treat as a single quantity. I mean, our methods, at least at this level, at the undergraduate level, do not allow us to distinguish between the product of these two parameters. I mean, they have, um, it's kind of difficult. I mean, actually, in principle, I would want to teach even the theory behind A, but I don't have the time, so I think I'll kind of skip it. Um, so in any case, as far as we are concerned, the flux from the gas phase to the cells is basically KLA multiplied by Ca star. This is for oxygen, where Ca star is essentially pi A over HA, right? Notice that the expression depends only on the bulk concentrations. We eliminated the interfacial concentrations. The model contains them, but as we analyzed the model, the interfacial concentrations disappeared because we solved for them, substituted them, and that's how we got the final expressions. Okay? And if the gas is highly soluble, as is the case for CO2, then you simply have to replace it by Kg multiplied by, and then it becomes, pi a minus pi a star, which is the appropriate, I think we've already gone through that, right? This is the appropriate expression to use if the gas is highly soluble. So if you're working with carbon dioxide, you can ignore the concentration on the liquid side and just you get Kg multiplied by pi a minus pi a star. Now, the last thing I'd like to point out is that this is just one theory um, for the mass transfer coefficient out of three. Actually, there are only two important theories. The second important theory is sort of worth mentioning, although I will not go into detail. Um, Now, the main assumption that the new theory questions is this assumption over here, steady state. You see, uh, when going back to this picture, what you have is basically, and I'll redraw it using basically green, you have a liquid film that is traversing over the bubble like this. A much more realistic assumption is that what is happening here is not that, the liquid moves so slowly that it spends a large amount of time and basically steady state develops. Instead, basically, the liquid film moves over the bubble for only a short period. There's a short contact time. And that means that the mass transfer is actually a transient phenomenon. For a little while, the liquid flows over it and then it disappears. And this is actually covered in your transport phenomena. Um, in the new edition, this is covered. I'll just mention it. So that is called, let me also say, so there is another more realistic theory of mass transfer across an interface. It does not assume steady state. So this theory is called uh, penetration theory. So here, basically, what you assume is that this is your interface, this is your gas, and here is your liquid film. Sorry, I should use the same. Now you assume here that liquid is flowing, right? And it has some velocity profile uh, where so actually I think the lecture is over, so but I'll just mention the reference. Maybe I'll cover it next time. This is from chapter 18 of Bird, Stewart, and Lightfoot, and it is called this is section 18, section 5, and that is page 558. Okay, so basically this is about accounting for the fact that there is only a small period of time during which the liquid is in contact with the gas, it never reaches steady state. So you're basically doing a transient analysis. That is all there is to it. And this leads to more realistic expressions. Instead of being proportional to the diffusion, to the diffusivity, it turns out that it is proportional to the square root of the diffusivity. So I think we'll pick up on it next time.
Sir,
Uh-huh.
sir, about the vivas for those who are ill. So should I get that scheduled for this weekend?
Man, I'm now really thinking that I can't do it because there are only about 20 days left, right, for the finals.
Yes, sir.
And it would be crazy for me. So I just cannot, right? I mean, it is what it is. They have to learn to live with one evaluation now.
Oh, so
I think
they'll just one
because
evaluation for 100
that's
marks.
it. That's it. Because I mean, tough luck. Because I tried multiple times, right? I mean, it just hasn't worked out. I would have happily done it over the midterm break too, but that is also sacrosanct. People don't want to, uh, you know, midterm break is sacrosanct. But now I'm told November 10th is the last date of class.
Yes,
So,
sir. Let me just yeah.
it doesn't sound to me reasonable that I'm,
Sir,
continuing to
November,
hold
yeah, November 11th is the last day of class.
and besides, I have massive extra teaching that has just come to me because a faculty member has resigned. So I have really no time now. I'm teaching two courses effective next week.
So Professor Rohan Jain.
So I have to teach his course and this course, and that I don't have time to conduct exams now.
So
This
sir,
is all I'll do.
how will you conduct the major?
Well, I'm tempted more and more to do the same way because I'm not convinced that a written exam. It kind of depends on how many people have onboarded. If most people have onboarded, then I will maybe hold an exam in the normal mode, right? Do you understand? Like sitting in a class. Uh,
Yes, sir.
and the ones who say they have not onboarded, for them I'll hold vivas.
Okay, sir.
This
Sir,
is
but
the way I'm.
can you like manage some like two evaluations for those who are ill because otherwise it will become very difficult. And so even for the class committee meeting feedbacks that I'm taking, many people are requesting some written assignment type evaluation. Otherwise, some people won't be able to get marks at all.
I this written assignment and all this stuff. This is just a complete sham, right? I mean, do you understand? The whole purpose of holding the Viva was that this copying on such a mass scale. That it became clear to me last semester that it's the honest people who are suffering. Do you
Yes, sir.
understand my
Yes,
point? I
yes.
just felt
But
that there's something
sir,
wrong about
some
the picture. Yeah.
yes, sir. But some people have also said that they're nervous while giving the viva, so they're not able to give the answers correctly, or they fumble up. And, some have
Yeah, right.
communication issues.
Somehow that's I have given at least 20 minutes to each person.
Yes, sir.
Uh, I mean, and people who have fumbled. I mean, look, I've been doing this for far too long. Do you understand my point? I didn't get into this game like last year. So I can tell a lot more from talking than I can from grading. Grading is like, hey, you write some shit and throw it on my face, and I have to figure out what the hell you wrote. But while I'm talking, within 5 to 8 minutes, I pretty much know where you stand. Do you follow what I'm saying?
Yes, sir. Yes, sir. I follow this.
Yeah. I think it's the fairest way to do it. And I wouldn't because it's costing me far more time. I mean, no faculty member is doing this. They're
Yes, sir.
all quite happy to just go along with a, huh. I mean, I know of no faculty member, and some have even come and told me, you're crazy. Who cares if they copy? But I have a real problem with the way people are copying, right? I mean, last
Some
semester I found almost, out of a total of 30, I could easily count almost 20 people copied, 20,
yes, sir.
25. So, matlab, this is good. This means that at least in my course, you work. Nervousness, man. I mean, I'll give you 20 minutes. Or time, Lelo. What is the
Yes, sir.
problem?
Yes. Sir,
And
so like Preeti ma'am had set up separate papers and individual questions for everyone in the written. So there was no copying on her paper either.
you think
So,
I can do that for 55 students? You think it's
uh,
reasonable?
mm,
Should I give
mm,
55 different questions? I mean, I have to come up with new questions for every Viva session. So the
oh
questions are
yes, sir.
transmitted within 20 minutes.
Yes, sir, yes.
You want me to set up 55 different questions? How would
No,
I do that?
like just slight variations enough so that people don't have time to copy something like that.
Well, I'll see. Maybe I'll
And
change
and
numbers
such
or something.
and so Shilpi ma'am had a written like typed section on Moodle, so then she was able to get the similarities and penalize the people accordingly. She had that, but it's not a descriptive code.
No, but how can I? I'm not asking you to tell me, the difference between prokaryotes and eukaryotes, right? I mean,
Yes,
I
sir. Yes,
have.
sir.
So I'll see. The only thing I can see is numerical problems with randomized numbers. But how long does it take to transmit your solution? I mean, one WhatsApp message is all it takes, right?
Yes,
I
sir.
mean, just one photograph and you have the solution. So why is there so much resistance to this? This is much more work for me than you, right?
So there is
People have,
resistance from some people. I mean, I am quite happy with this, but some people just can't get marks like this from the Viva, so they're afraid that they'll fail or they'll have to withdraw.
well,
So
whoever did poorly, I had a long conversation with them and I told them exactly what they got. Most of these are people who had not attended the lectures, who had not listened to them thoroughly, and basically had a fairly superficial understanding of what was done. Did you understand? And right from the beginning, I've said that this is not like your standard DBEB courses. This was made very clear. I cannot do
yes,
any more than that. Huh. So get used to it, right? Because I mean, sometimes you deal with real people in life, right? You can't always fudge your way through it. So this is it. I mean, if you know your stuff, you really should have no problem. I can just tell you this: that there were people who aced it, right? If the stuff that I was doing was so thoroughly profound, then basically everybody would have gotten bad scores. What I'm telling you is there are people who aced it. Is that
okay,
clear?
sir.
I mean, are you following? Yeah,
Yes,
there
sir.
are people who scored a 90 after a 20-minute grilling, and there were people who could not even answer the first question I asked. So there has to be something, right? I mean, I have to make a distinction. People could not even explain to me the first stuff that I did in the first three lectures. So these differences will be indicated in the scores. So I'll see. Maybe have maybe some way of some written part, but only if you attend the exam in person. I'm not giving any exams that you do while sitting at home.
Yes, sir. But sir, for example, like there is a provision for reminors and remajors. Then will you be conducting, for example, if some people skip their majors because of an illness, then uh, you'll be taking
Yeah,
care.
इतना नहीं हो सकता है. And so they have skipped their major and minor. I mean, is
Yeah,
that what you're telling?
if that happens, yes, sir. Like
Boy, I mean, you're really stretching it now, right? I mean,
like
so
for
I
example, that even if
uh,
for so I gave my minor, but if I get ill during the major, then I would like to give my major then I'd like to give my major and not just be graded on my minor attempt.
mm-hmm.
Yes, sir.
So, I will give a remajor, but I'll be doing it very, very carefully. Do you realize how many people skipped the minor?
Yes, sir. I
Do you have
realize
any
how many.
idea of the numbers?
Yes,
Do you
sir.
have any idea of the numbers? Yeah.
Yes. So you
Then
said
it's not
14, and I think it went up to 15, 16, I think.
out of a total of 55.
Yes, sir.
Uh,
That's
doesn't that sound like an unusually high number? Is 30% of India suffering from disease?
no, sir. But yeah, I mean, these people would now know that not to miss the majors because that's their only last
So,
chance.
मतलब I, I mean, and what is really amazing is that the number of people who got sick immediately after the Viva began. I mean, it's unbelievable. The Viva started on a Saturday, and as soon as the word went out that he's hammering the crap out of people, boom! I got like 10 sick people within 6 hours, and I'm thinking, wow, from 55 we've gone to, I mean, by Sunday, I had 13 or 14 sick people in a class of 55. I mean, the disease was really spreading. I mean, you think I'm a moron? I mean, you think I can't follow what I'm saying? I mean,
Yes,
does
sir.
that
But
sound reasonable to you? 14
no, sir.
out of 55. Just do the numbers, yeah. It's
Yes, sir. Yes.
25%.
Sir, but at least those who are genuinely ill, because I know some people who were actually admitted and went to the hospital and got all the tests done. So can they at least get an attempt at the second minor, literary minor?
Well, and will you help me distinguish between the ones who are honest and the ones who are not?
Yes, sir. I'll do that. Yes, sir.
Well, why don't you do that then?
Okay, sir.
If I have authentic cases, I'm happy to take it up. But my life
Yes,
has been made hell by the fact that 25% of the people didn't show up.
yes, sir.
With all kinds of reasons. I mean, some of them were like sick for a day and then 2 days later they showed up. Some of them just disappeared off the map. You find out the real from the fake and then, we'll give it a chance. But I mean, the bottom line for me is that I'm swamped. Now I have 6 lectures a week, plus 2 exams, not just this course, but also the other course.
Yes, sir.
And so I'll see how I work it out, where I find the time.
Yes, sir.
Okay.
If you find the time, just please mail me or put it on Teams. Then I'll just schedule in some people.
It will have to be over a weekend because I have no time during weekdays, right? I have one
Yes,
lecture
sir.
every day.
Yes. So,
Okay.
sir, are you
All
free
right.
this Saturday and Sunday?
Not yet. I don't know because I don't know when I'm supposed to start teaching Rohan Jain's course. I was supposed to start teaching the latter part of the course, but now I'm being told I have to teach effective Friday. Is that a course that you guys are taking, or is that somebody else?
No, sir. No, sir. It's somebody else. No, it's not us.
Sir, I guess it's our senior batch.
So that course may begin for me on Friday, which is tomorrow. I'm trying to
Yes, sir.
avoid it, but they're telling me to start teaching the course starting Friday. In which case, from now until at least the next 10 days, I have no time. Right? It's 6 hours of lectures a week, right? 1.5 hours each on this, and then 3 hours on that. And I'm kind of a little overwhelmed. So I'll see. I'll let you know. But once again, this will be the last chance. Do you
Yes, sir.
understand? This
Yes, sir. Yes,
this
sir.
endless I'm sick, is getting a little. It's getting a little bit too much for me. Okay. All right.
Yes, sir. Thank you, sir.
Uh,
Thank you,
okay.
sir.
Good afternoon, sir.
Thank you, sir.